In this Math Counts Preparation Lesson, we are going to be talking more about geometry, so let's get started. So, we are going to be using lots of triangles in today's Math Counts Preparation Lesson. First thing we gotta talk about is similarity, or similar triangles. Now, similar triangles, we're going to be focusing on AA similarity today because the other two similarity theorems are not going to be present too much. So for today's video, we're just going to be focusing on AA similarity, which states that if two angles of a triangle, if two pairs of corresponding angles are congruent, so let's say we have angle X over here, and this is Y, and this is Z, and we have another triangle over here which has corresponding angles. So if we turn this triangle, let's say if we were to turn this triangle, Z could correspond to some angle over here, which would be called, let's say Z corresponded to, let's say, another angle called A. Now by AA similarity, if corresponding angles are equal, they're similar. So this could be X, this could be Y, and this is by the degrees. The degrees, and I'm going to put this as to mark it, like these are congruent, and this doesn't have to be named X and Y. We can name these something different. We can name these B and C. So this is angle-angle similarity. You're going to be using this a lot in geometry problems. Now let's move on to arguably the most important part of geometry, or one of the most important aspects of geometry, which is special right triangles. Now, we have two types of special right triangles, and if you're actually interested in learning more about special right triangles, or I'll link the videos down in the description. I have videos on some proofs proving why the relationship between the sides of special right triangles, certain special right triangles, are actually true. But here's the actual thing. So let's talk about isosceles right triangles, or 45-45-90 triangles. So whenever you have an isosceles right triangle, when the two legs are congruent, this angle is going to be 90 degrees, and these two have to be equal since it's an isosceles triangle. So they have to also be complementary since it's a right triangle, so we have 45 degrees and 45 degrees over here. Now 45-45-90 triangle is one of the most special triangles out there because, first off, the legs are the same, and the hypotenuse is x times the square root of 2. That's the 45-45-90 triangle. The hypotenuse is always the length of the legs, any leg, because they're equal, multiplied by the square root of 2. X root 2 is the hypotenuse of a 45-45-90 triangle. Similarly, if we had a triangle, if it's not really similar, but another special right triangle would be a 30-60-90 triangle. This is not the best triangle, but it works. So, 30-60-90 triangle. This is also one of the most important triangles, most special triangles in geometry. So let's say this is the shortest leg. Let's call the shortest leg X. The longer leg is the shorter leg multiplied by the square root of 3. and the hypotenuse is the shorter leg multiplied by 2. Very special triangle, as you can see. So obviously, these two triangles are pretty special in geometry problems, and often we like to use angle bisectors to build these triangles to help us to figure out side lengths. Especially, these are very important side problems when you have to find side lengths. So always remember your special right triangles. These are the only two there. But if you are interested, I do have, as I said, proofs of these two, why the relationships between the sides are true, down in the description below. Now, in today's video, the problems we have are a little centered around angle chasing, side length chasing type of problems. Here's some more tips, because angle chasing can be hard for some people. In fact, most people find it hard at first, angle chasing. So, let's get into the tips. 1, always look at the sides. When you're looking at the sides, you always want to see, is there a common side that's equal? Can I build some more triangles, etc.? Another sort of a tip I would give is look for similar triangles. We discussed a similarity, and if you have parallel lines, whenever we have parallel lines, we're going to have some sort of similar triangle. So always look for your parallel lines. Those are parallel lines. Now, parallel lines means we have similar triangles. If we have parallel lines, most likely, most of the time we have similar triangles. Always look out for special right triangles, right? Special right triangles are, as we talk, let's say I have a triangle like this. I have an obtuse triangle here. Alright, let's say I have an obtuse triangle. And let's say that this is 120 degrees. Right? And this is 30. And this is 30. I can build using an angle bisector, right? A bisector cuts an angle in half, so this no longer has to be 120 degrees. We can use a bisector. This is the 120 degree angle. We can cut it in half and then draw a line perpendicular to this segment right here, which will build a right angle here, and this also has to be a right angle. This is bisected. 120 divided by 2 is 60. Guess what we have? 2 30, 60, 90 triangles. So always look out for your bisectors. Another useful trick is trying to trisect, trying to break up angles into smaller pieces. Now, let's move on to the problems. In the drawing, EBC is an equilateral triangle and ABC is a square. Find the measure of angle BED. This is from the 1987 MAO. Old problem. But it's an interesting problem in the sense that this problem is actually interesting because I think it's probably interesting because you don't really have angle BED is from here. So angle BED starts over at B and goes down to E. And then it goes like this. So that's really angle BED what we're looking for right now. That's the angle. So this problem is pretty interesting because we don't really have sort of a good way to find BED right off the bat. We do know we have a square and we have an equilateral triangle. So these are all right angles. And equilateral triangle means, the diagram is pretty small, but if we build what we're supposed to have, these are all 60 degrees. Of course, BED cuts our 60-degree angle. Not equally, but it's cut. Now, let's check out this triangle that's formed over here. We have a triangle built by this angle. Now, let's try to find some angle measures. We have DCE over here, which is right angle 60-degree angle, 90 plus 60. This is 150 right there. 150 degrees. Now, I set an angle chasing tip. Try to look at the sides. Common sides. I see a common side right here. Equilateral triangle. Square. This tells us that this is equal to this. That means this is isosceles. So that tells us that these angles right here are equal. So we have 30 over here. And if you're not really getting it, this is our triangle that we have. Our smaller triangle, we have 150. And we just found out that this is isosceles, and this is the side of an equilateral triangle, and this is the side of the square, and they're equal because they share a common side. And all the other sides of the corresponding figure are equals. That means this is also 30 degrees. To build, actually no, the sum is 30 degrees, so this is 15 degrees. My bad. 15 degrees. And these two are 15 degrees because they build the sum of 180 degrees. Now, we can look at our diagram, and I'm going to erase all this mess since we're way cleaner over here. We know that we're trying to find BED. Right? We have a triangle over here. If we turn our attention from here, we can see that we can build a similar, a triangle that's pretty similar by going like this. And not actually like similar, like close to what this is. So we have another one. This measure is again 30. This measure is 15. This measure is 150. And this measure over here is, of course, 15. Now notice that the entire thing over here is an equilateral triangle. This is 60 degrees. Over here, partially, it's cut by a 15-degree angle over here and a 15-degree angle over here. And we can see that this angle over here is 30 degrees. We're trying to find BED. Now this angle right here, this angle like right over here is 30, and it's surrounded by some 15-degree angles. We're trying to find BED. So to do that, we just sum these two to build BED, and we get 45 degrees. The diagram was kind of small, but we still did it. Let's move on. So I think the main thing about this problem is it's a little more, I guess you could call it advanced, even though, like, it's the 2000 AMC 10. Problem number 7, but it's a very interesting problem. In a rectangle ABCD, AD is equal to 1, and point P is on AB, and DB and DP trisect angle ADC. What is the perimeter of triangle BDP? So we're trying to find the perimeter of this triangle right here. This triangle right here, BDP. And we know that AD is 1. Now, we see that we look to be stuck. We don't know any other things. All we know is 1. And you might think that they didn't give you enough information. So I want you to see what are we supposed to do next? Think of some ideas. Alright. The first thing I see is, instead of sides, I see angles. In rectangle ABCD, rectangle, all right angles. A right angle over here. A right angle over here. Alright. And this angle ADC is trisected. Trisected, cut into 3 equal parts. This means that this is 30, this is 30, and this is 30. Now, 30, 90, this has to be a 60-degree angle. These two build a straight line. This has to be a 120-degree angle. Over here, let's go to this triangle. 30, 90, this has to be a 60-degree angle. And these two are supplementary. This has to be a 30-degree angle. Isosceles over here. Now, why are we marking angles? We mark angles to figure out sides, side lengths. we're looking for the perimeter of triangle BDP. Let's try to figure out some side lengths right off the bat. Let's take a look at this 30, 60, 90 triangle. We have 1 as of a long leg. Now to obtain the shorter leg, we have to multiply the shorter leg by the square root of 3. Now the only way we're going to do that is if we take the square root of 3, divide by 3, and we multiply by the square root of 3, well, this is just square root of square root, which gives us 3 over 3, which is equal to 1. So this tells us that this is the square root of 3 over 3. Right? Alright, now let's use our eraser, erase some computations that we did. Moving on. Let's try to find this hypotenuse right here. We know that this is double this, so this has to be 2 times the square root of 3 over 3. Right? That's what it has to be. Now we've figured out the lengths of this triangle. Let's move on to our other 30, 60, 90 triangle over here. We have a 1 as the shorter leg, and the longer leg is 1 times the square root of 3, which is just the square root of 3. This tells us that AB is also the square root of 3. And we don't even have to proceed. We know that this entire thing is the square root of 3. Well, we do have to keep proceeding over here. So we have 1 multiplied. The hypotenuse of triangle BCD is just the 2 multiplied by the length of BC, which is 2. Now all we need is PB and we're done. Now, check this out. This entire length is the square root of 3. Now take a look at AP. AP is 1/3 of AB. If the AP is 1/3 of AB, PB is 2/3 of AB. Right? 2/3 of AB. So you have 2 over 3 of AB. AB is DC, and DC is the square root of 3 over 1. Right? So over here we have 2 root 3 over 3. 2 root 3 over 3 is what we have. And this works out. Since we've added the square root of 3 divided by 3 over, plus 2 root 3 over 3, we're going to get 3 root 3 over 3, and the 3's cancel out, so you're just left with the square root of 3, which works out. I forgot to label this. There we go. We have all of our side lengths. Now, how are we going to proceed with the problem? Well, how are we going to proceed with the problem? We just add our lengths up. 2 times square root of 3 plus 2 times square root of 3, that's 4 times square root of 3 over 3. So we have 4 root 3 over 3. And we have this hypotenuse is 2. And this is simplest radical form. So this is our answer. That is the perimeter of triangle BDP. Let's move on. We have a figure at the right. AB is equal to BC is equal to 1. AD is parallel to BC and CD is parallel to AE. Find AE. Problem credit goes to math counts. Math counts problem here. Suits the lesson. Now, AB is equal to BC and they're equal to 1. We have a right angle. Isosceles right triangle. 45. This is 45. And we know that this hypotenuse, which is also a leg of this right triangle over here, is equal to the square root of 2. Okay. Let's see what we have. Let's see what else we have. We have that AD is parallel to BC. This is probably the most powerful problem-solving tactic we can use here, which is triangle similarity. If they're parallel, we see some similar triangles. We see that ABC is similar to triangle AED. Now, if they are similar, we don't know the ratio yet, but we don't need the ratio. If they're similar, this has to be isosceles. This is 45. Isosceles right triangle. Right? That has to be similar. Now, let's take a look at this triangle right here. We see that over here we have a right angle. We have 45-degree angle surrounding it. And, well, look for more similarity. We see CD is parallel to AE. CD is parallel to AE, CD, AE. We see some more similar triangles. If these are similar, this has to be isosceles, which tells us the leg is the square root of 2, and more importantly, the angles. This is a right angle, which makes sense. It also looks like a right angle, but this is a right angle. Never assume in geometry also. Square root of 2, square root of 2. Check this hypotenuse out. The hypotenuse is the square root of 2 multiplied by the length of a leg. This is the square root of 2 multiplied by the square root of 2. This gives us 2. Much more cleaner than the radicals. We have length 2. And of course, the hypotenuse will be 2 times the square root of 2 multiplied by one of the legs, which is 2 times the square root of 2. We're looking for AE. AE is this hypotenuse right over here. So we have our answer as 2 times the square root of 2. And that is the solution to this problem, or a solution. Problem has lots of solutions. Hopefully this video is helpful. And yeah.